Okay, so good afternoon, everyone. Welcome back to the week nine's discussion hours. And as you know, or as we said in the last week, today we'll be starting with a different mode of heat transfer, which is radiation heat transfer, as you can see on your screen. And we will begin the formal understanding of radiation heat transfer, as I said, by looking into the introductory concept associated with radiation, although the details of which you have already witnessed in this week's this I mean live what to say the lecture series. But we'll begin by giving you a recapitulation of the basic introduction of to radiation heat transfer, and then we will formally move on to the different kinds of radiation fluxes and some associated numericals and concept associated with these radiation fluxes. And if there is time at the end of at the end of today's session, we will look into the concepts which are known as intensity of radiation and spectral and directional dependence. Okay, so this is the agenda for today's session, and without any delay, let's get started. So as you have seen in the week's discussion videos, that we will primarily be learning a different mode of heat transfer now, which is known as radiation, and some important fundamental concepts that are associated with radiation, which is different from the other two modes of heat transfer, which were conduction and convection. Was that the first thing that comes into our mind is that radiation is two directional, which is the first stark difference that you will witness when you compare it with conduction and convection. By two directional, what I mean is that, let's say there is a body uh, denoted by a surface temperature, let's say Ts, and there is, let's say, another body which is enclosing the smaller body, which is now, let's say, the temperature, we'll call it as the surrounding. Okay. So when I speak about radiation exchange taking place between these two bodies, there is actually heat transfer taking place from, let's say, the first body, we will call it as body 1, and the surrounding, or the second body, we will call it as body 2. And what I mean to say is that when I say it's two directional, is the fact that there is radiation exchange taking place from the first body, that is the smaller body, that is 1, and it is exchanging radiation with body 2, and also there is radiation exchange taking place from the surrounding with the first body. So what we saw in conduction and convection is that there is a definite direction of heat transfer that takes place. For instance, in conduction and convection, the direction of heat transfer is from the body which is at higher temperature to the body at lower temperature. But in case of radiation, it is not it is not just one directional, but actually there is radiation taking place between the two bodies. Okay, so the first thing is that, as I said, it's two directional. The second thing is that now, if the scenario is such that let's say the temperature of the first body, that is body 1, is greater than the temperature of the second body, then we define something which is known as radiation. So we define something which is known as net uh, radiation exchange, and this net radiation exchange will be from body 1 to body 2, and 1 will equilibrate. Okay, so because radiation is a two-directional phenomenon, so we define something which is known as a net radiation exchange. And this net radiation exchange will be from now the body at higher temperature to the body at lower temperature. But that's the word net, which is very important, that comes into the picture here, because of the fact that it is always two-directional in nature. Okay, so in principle, when we say there is radiation exchange, we actually mean the net radiation exchange taking place between bodies. Okay, all right, that's the first idea. The second idea that we know, and that you had been uh, already mentioned, is that radiation heat transfer take place without the presence of any material medium. So it doesn't require any material medium. So if there are two bodies in vacuum, they can exchange radiation. Okay, it is owing to their own surface temperatures in general. Okay, so it does not require the fact that there is so it doesn't take care of or it doesn't specifically require any material medium for its propagation. That's the idea that I wanted to convey. Okay, so irrespective of the presence or in the absence of a material media, there will be radiation exchange taking place between two bodies which are at temperatures 1 and temperature 2. Okay, and there will be the net exchange of radiation because again of the fact that radiation is two directional in nature. Okay, second thing, we generally will be exposed to a very particular word which is known as emission. And if you actually try to understand how emission takes place, so emission in principle is a volumetric phenomenon because radiation is basically associated with emission, and we will quantify this emission in a very short while. But when we in general speak about the word emission, it is in principle a volumetric phenomenon. Okay, but in solids and liquids, so let's say we are talking about, let's say we are kind of talking about a solid of interest, the emission from the molecules which are inside the solids, okay, the distribution or the emission which takes place due to the distribution of the molecules. So the interior molecules that are present inside the solid, let's say inside a solid or a liquid, the emission from these interior molecules that are taking place, these are generally absorbed by the other molecules. Okay, so which means if the emission from the interior molecules that are inside the solid are absorbed, this means that the only you know the only emission that will actually matter is actually the emission from the surfaces. Okay, so surface emission actually matters. So although emission is a volumetric phenomenon taking place due to all the molecules present inside a solid or a liquid, but the emission from the interior molecules of a particular solid or a liquid is generally absorbed within the solid or the liquid, which means the only emission that actually matter in radiation heat transfer is the emission from the surfaces. And that's why in practical scenario or in practical senses, we will consider emissions as surface phenomenon. Okay, so this is what we will consider in practical scenarios. Okay, so although in principle it's a volumetric phenomenon, but in realistic scenarios or practical scenarios, we will consider emissions as surface phenomenon. Okay, all right. So now we begin our understanding of actually trying to quantify this emission. And the first approach, in general, as I would say, of quantifying this emission is by trying to understand the radiation fluxes. As you can see from your screen, so there are a couple of radiation fluxes that you need to understand in order to actually try to basically quantify this emission when we basically talk about radiation exchange taking place from a surface. Okay, so in a quest to actually uh, so basically, in order to quantify these radiation fluxes, we will consider, let's say, a surface and a solid. In particular, it's a solid that we'll consider. It may be also a liquid, but I mean, in general, in this course we will basically stick to radiation exchange taking place from solids. So we'll consider a solid, and on this solid, you can see that there is a irradiation that is falling with a magnitude g. So first of all, this irradiation is actually a flux, and we will start by first trying to define what is irradiation. Okay, so the first thing, which is the irradiation, this is actually the incident radiation on a surface per unit area. Okay, so what irradiation says is that, so you can think of it like there is a surface. Let's say the surface is at some arbitrary temperature T. Now, whatever the other radiation fluxes emitted by all other surfaces, which is kind of like a surrounding to the considered surface of interest. So the radiations from the surroundings that fall on the surface, they are basically known as irradiation, and that is, so irradiation is kind of, so you can interpret like it's an energy per unit like area. So it's so we'll define it like so the letter that we will use to define irradiation is G, and this G has got an unit of watt per meter square. Okay, and we will define this irradiation as the incident radiation on a surface per unit area. Okay, so first of all, as I said, you should have a question that should arise in your mind, that where from this incident radiation come from, where from this incident radiation actually come. So as I said, so you pick the body of your interest, let's say this this particular solid. This solid, let's say, is at some temperature T. Then all other objects which are at some other given temperature will serve as a surrounding to this particular solid of interest, and the radiations that are emitted from all other objects which serve as a surrounding to this particular objects of interest, those radiations that incident on this surface, I mean those are, that is in principle is what we call it as irradiation. Okay, so and this irradiation has gotten unit of watt per meter square, so it's kind of, so it's kind of a flux quantity that we are actually trying to specify. Okay, now the important thing that we need to understand for this considered body which is of our interest is the fact that whatever the irradiation that is incident on its surface of the body of our interest, it it basically can go through three possible ways. So from the incident irradiation that falls on this surface, some of this can be transmitted through the surface. For instance, let's say in glass, the amount of irradiation that falls on glass, most of its part is basically transmitted through it, because it is kind of a transparent surface, and some part of this irradiation which does not get transmitted to it can actually get absorbed inside the surface, or some part of it which does not get transmitted or absorbed, those basically gets reflected. Okay, so if you now kind of do a energy balance for this incoming irradiation, then you can say that this G, the incoming irradiation, is basically equal to the transmitted part of irradiation plus the absorbed part plus the reflected part basically. So then I can write this in mathematical terms as G is basically equal to GTR, which is the transmitted part of irradiation, plus GAB, which is the absorbed part of irradiation, plus GREF, which is the reflected part of irradiation. And these are the only three possibilities which can happen to this incoming radiation. It can get absorbed, it can get transmitted through it, and it can get reflected. I mean, these are the only three possibilities that can happen, and you can verify this just by doing an energy balance for this particular solid of interest. Okay, now what we will do is we will divide this. Let's say I call this as 1. So we'll divide this 1 by G, and then I can write this as GTR by G plus GAB by G plus GREF by G is equal to 1. Okay, we are just dividing the entire, so we are just dividing the entire expression by G. So now if you pay a little bit of attention, then you can see that this quantity GTR by G, it says that, so first of all, it's kind of a fraction. It is a fraction because it is just the transmitted part of the incoming radiation. So it says that, so this fraction actually says that how much percent or how much part of the incoming irradiation is basically getting transmitted. And this fraction, we will denote this fraction as a so we'll denote this by the symbol tau. And the similar analogy can be drawn from the other two components as well. For instance, this quantity GAB by G speaks about the fraction of irradiation that is getting absorbed on the particular surface or the particular body of interest from the incoming irradiation. So we'll denote this GAB by G as a quantity which is known as alpha, and this the third part, which is the final part, it says, just by drawing analogy from the other two part, it just says that how much is the fraction that gets reflected from the initial irradiation that is incident on that particular body. And we'll call this G ref by G as a parameter which is known as rho. Which means I can now say that tau plus alpha plus rho is basically equal to 1. Equivalently, I can also say that this tau, alpha and rho, these are just fractions, and their sum basically goes equal to 1. That is just a result of the energy balance. So basically this tau, this is actually known as transmittivity. This alpha is known as absorptivity, and this rho, this is known as reflectivity. Okay. So now you can formally define these quantities, transmittivity, absorptivity, as reflectivity. For instance, you can define transmittivity as the fraction of irradiation that is getting transmitted with respect to, the incident radiation that is falling on the surface. Okay. Or in other words, when you are talking about when the word fraction comes in, you can just call transmittivity as the fraction of irradiation that gets transmitted through the body. Similarly, absorptivity is the fraction of irradiation that gets absorbed within the body, and reflectivity is the fraction of irradiation that gets reflected from the body. Okay. So this is the first conclusion that you can draw from the, so it's kind of, so basically you can say that so if you ask me what happens to the fate of the irradiation upon incident on a surface, so it just have three possible ways. Mathematically, these three possible ways are manifested through this equation as tau plus alpha plus rho is basically equal to 1. Okay. All right. Now, in this course, what we will basically assume is that we will consider the object of interest as opaque, and this implies that tau is basically equal to 0. Okay. So this is an assumption that we are assuming that all the heat transfer analysis that follows from now on will consider the body, unless mentioned otherwise, as opaque, which means it basically cannot transmit the incoming radiation, or in other words, its transmittivity is equal to 0. So it then follows that we can write alpha plus rho is equal to 1, or we can say that the reflectivity is just 1 minus of absorptivity. Okay. So this is true for opaque bodies. Okay. All right. Okay. So the second flux that we would define is something which is known as emissive power. And we will denote this as by E. Okay. And this emissive power is defined as the rate at which radiation is emitted from a surface per unit area. Okay. So you can interpret that emissive power is also kind of a flux quantity, because it is the rate at which radiation is emitted, which is watt per unit area. So it basically becomes watt per meter square. So then what does it mean? So it means that from this diagram, we can understand that because this body, which is of our interest, this body is also at a given temperature, let's say T, and this temperature is assumed to be greater than 0 Kelvin, it will also emit owing to its own temperature. Okay, so the emissions that takes place owing to its own temperature is known as emissive power, and those emissions which are calculated per unit area, precisely that is what the emissive power denotes. Okay, so and I hope you can now realize that this emissive power is a sole function of the temperature of the body. Okay, and mathematically this emissive power is, so basically it appears as epsilon times sigma times Ts raised to the power 4. Okay, where this epsilon, this is known as the emissivity of the body, and this sigma, this is known as the Stephen Boltzmann constant, and you can find its value as 5.67 into 10 to the power minus 8 with an unit of watt per meter square Kelvin to the power 4. Okay, so I hope you can realize that this emissive power is not a function of the incoming radiation. It has nothing to do with the incoming radiation. Rather, the emissive power of a body is just dependent on its particular temperature. In fact, I will call it as the surface temperature, because as I said that we'll assume in this course, at least we'll assume emissions to be a surface phenomenon rather than being a volumetric phenomenon. Okay, so if I now ask you that what is the emissive power of a surface, okay, you should then reply that it is proportional to the fourth power of its surface temperature. That's it. That is the only variable on which this emissive power depends on. Of course, it depends on the properties of the body, which is known as emissivity, and a constant, which is nothing but the Stephen Boltzmann constant, which is 5.67 into 10 to the power minus 8 watt per meter Kelvin to the power 4. And as I repeat, and as I have said, it has nothing to do with the incoming irradiation falling on the body. So given that now there are two things that are happening, one, the incoming radiation falling on a particular surface, and owing to its own temperature, there is an emissive power that is associated with it. So then it becomes customary to define the third flux, which is known as radiosity, and we will denote it by the variable J, or the letter J, and this is defined as rate at which radiation leaves a particular surface. And of course, this is also calculated per unit area. Okay. And I'll not just write repeatedly, but again, since it is calculated per unit area, it has also got an unit of watt per meter square. But I hope you now understand that if I now try to quantify how much radiation leaves a particular surface, I now need to understand that it is not just the emissive power, and it is not just the reflected part of the incoming radiation. Rather, it is the summation of these two things that gets combined to give you that basically combine to give you radiosity. So you can then interpret just from this physical scenario that your radiosity is so basically, if you look into this figure, I think it will be more clear. So the radiation that basically leaves this surface is equal to the reflected part of the irradiation plus the emissive power, which occurs because of the body that is present at a particular temperature Ts, or because of the surface temperature of the body, which is T, or let's say I'll call this surface temperature more precisely as Ts. Okay, so the radiation that leaves a particular surface, this comprises of two things: the reflected part of the incoming irradiation, which is G, and the emissive power, which is basically E. Okay, so then you can write this J as E plus plus what? Plus you can basically call it as G ref. Okay, and we know that this G ref is nothing but the reflectivity times the irradiation G. And now what we'll do is, so basically that's it. That's actually the most fundamental definition of radiosity. And what we'll now do is we'll do a little bit of simplification. So what we will say is that for opaque bodies, as we have discussed above, we can say that rho plus alpha is basically equal to 1, and then we can write rho as 1 minus alpha, which means the radiosity just simplifies to the emissive power, which is E, plus 1 minus alpha times G. And then if we use the definition of emissive power as this, and this is actually known as the Stephen-Boltzmann's law, we can then write the radiosity as epsilon times sigma times Ts raised to the power 4 plus 1 minus alpha times G. Okay, so this is true when tau is basically equals to 0. Okay, or we are considering the body to be an opaque body. Okay. By the way, you need to understand that this is actually known as Stephen Boltzmann's law, and there is also something which is known as the emissive power of a black body. So in case of a black body, what happens is that this emissivity becomes equal to 1, and we'll discuss this further more clearly in the next subsequent discussions. But you can then interpret that epsilon equal to 1 is the case for a black body. Okay, and then we call this E as EB, which is the emissive power of a black body, and this just becomes equal to sigma times Ts raised to the power 4. And I hope you understand that emissivity is a fraction, which means a black body has the maximum emissive power. And we will discuss this in details in the subsequent discussion that follows after this, after the discussions that we will have now. But anyways, I hope you can realize that now at least the radiosity, which is the net radiation that is leaving a particular surface, this comprises of two things. First, the emissive power, which takes place owing to its own surface temperature, and the reflected part of irradiation that that is basically equal to the reflectivity times the irradiation. Okay, and this form gets simplified for opaque bodies when we use the fact that my reflectivity is equal to 1 minus of alpha, and then this is what we get if we do the substitution, and then using the definition of emissive power as just epsilon times sigma T raised to the power 4. Okay. All right. So just giving you a recap. So what we did is we first defined irradiation that falls on a surface. We then define something which is known as emissive power, which is the flux that is associated with the own temperature of the body. And then we said that what is the radiation that leaves a particular surface. And then the last thing that we should do is define something which is known as the net radiative flux. And as you can see, as the word suggests, the net radiative flux is nothing but the net rate of radiation leaving a surface per unit area. So you can very easily now say that this net radiative flux is going to be the radiation that leaves the surface, which is radiosity minus the incoming radiation. That's it. That is precisely the amount of net radiative flux that basically leaves the surface. Because that's simple, right? Because whatever that is going out from the surface is denoted by radiosity. Whatever that is incident on the surface, that is denoted by, the irradiation. So the net radiative flux that goes out from the body is basically what goes out minus what comes in, and that is basically equal to, the radiosity minus irradiation. And I hope you can understand now from this figure as well, because this and this gets combined to give you radiosity, which is J. So if you now tell me what is the net radiation exchange, it will be just this J minus basically this. Okay, irradiation is the net flux that basically goes out from this body. Okay, that's just simple. So this you can infer just by using simple mathematics. Okay. All right. Now, if we just substitute this expression of J into here, what we'll get is that the net radiative flux is sigma epsilon sigma times Ts to the power 4 plus 1 minus alpha times G minus G. And then this is true when in the case where tau is basically equal to 0. This you need to understand. And then we can simplify this as G minus alpha G minus G. So this G and G gets cancelled. So the net radiation exchange, which is denoted as the net radiation flux, is basically equal to epsilon sigma Ts raised to the power 4 minus alpha times G. Okay. So this is the net, radiation exchange taking place for any opaque bodies. That is something that you need to understand. Okay. All right. And this net radiation exchange, we will denote it by something which is known as Q double prime of RAD, and this will denote the net radiation exchange taking place from a particular body. Okay. All right. So this is the overview of the 4 fluxes of that basically you need to understand. I call it as the 4 fundamental fluxes that you need to understand when you are when you basically try to quantify radiation heat transfer. And just by recapitulation, what we learned is first we define irradiation, then we define the emissive power, we then define radiosity, and finally we define the net radiation exchange taking place from the body, which is nothing but just the radiosity minus the irradiation. All right. So I hope this is clear. This is just fundamental stuffs, and a glimpse of this you have already witnessed in this week's video series, video lecture series. So what we'll now do is, which is actually the objective of this session, is that we will solve a problem. It's a nice problem that we'll solve that is associated with these radiation fluxes, and then it will give us an idea of how to basically use these fluxes, use the knowledge of these fluxes to basically calculate the certain things which are delineated in this problem. Okay. So from your screen you can see that it says that the top surface of an L equal to 5 mm thick anodized aluminum plate is irradiated with an irradiation of this much magnitude while being simultaneously exposed to convection conditions characterized by H and T infinity. Okay, so there is an aluminum surface with some thickness of 5 mm. This is being irradiated with an irradiation of G equal to 1000, and in addition to that there is a convective cooling or a convective heat transfer that is taking place owing to the fact that the ambient has a temperature T infinity, and the heat transfer coefficient associated with this is H infinity, which is of magnitude 40 watt per meter square Kelvin. Okay, it then says that the bottom surface of the plate is insulated, which means that this surface is insulated, which means that it's an opaque surface and there is no transmission taking place from this surface. And then it says that for a plate temperature of 400 Kelvin, that means that you can assume the surface temperature of this plate as 400 Kelvin, as well as its absorptivity, which is denoted by alpha is equal to 0.14 and emissivity of 0.76. The first thing that they're asking is to calculate the radiosity, which we denote it as J. The second thing that they're asking is to calculate the net radiation heat flux at the top of the surface. So they are basically asking you to calculate Q. I think we have denoted this Q by small, so we'll denote it as by a small q. So they are basically asking you to calculate the fourth flux that we define, which is Q net red, basically this. Okay, and then these are the two things that they're asking. And then what they're asking us is the fact that the rate at which the temperature of the plate is changing with time. Okay, so So I hope you can understand. So the first and the second things are simple. So given that there is an irradiation, given that the plate has a surface temperature of this much, you can calculate the radiosity and the net radiation exchange. But you also need to understand that because there is a heat transfer taking place from this body, owing to radiation and convection, because of the fact that it is also exposed to an ambient temperature of T infinity and heat transfer coefficient of H infinity, there is also convection heat transfer taking. Now, because of these two heat transfer, overall the temperature of this plate will change with time. We will basically neglect the spatial variations of temperature. That is, we'll neglect the temperature as a function of the spatial coordinates of the body. But because of heat transfer taking place, you can you can assume, or what you can also do is that you can calculate the bio number associated with it. For instance, you can calculate this and you can establish the fact that your bio number is less than 0.1, which means that you can ignore the spatial variations taking place inside the body. But because of the heat transfer taking place due to radiation and convection, the temperature of the body will basically change with time. Okay, so the third part of the question is asking you to calculate this temporal evolution of temperature with time. Okay, this is what will require. So let's first do the first and the second part, and then we will systematically do the third part, for which we require a little bit of more deeper understanding of the subject. Okay, but anyways, I will let you to read the problem on your own once again, and then we'll proceed with the solution of this problem. Okay, all right, so let's get started. So first of all, what we need to do is we need to evaluate the radiosity J, and as we have defined that my radiosity comprises of two things. First, the emissive power, which we call it as E, and then the reflected part of the irradiation. Okay, but again we can now assume that because the bottom surface of the plate is insulated, so you can assume that it's an opaque surface, which means that my tau is basically equal to 0, and this we are assuming since since so what you can write that since the bottom surface is insulated, and you are assuming that and the body is opaque, which means I can then say that my alpha is going to be 1 minus of rho. This is from the fact that alpha plus rho is equal to 1 since tau is 0. And then I can now write this radiosity J. See, we are doing this because in our question we are given alpha, not rho. So we now need to relate rho with alpha, and that's how we can relate rho from alpha. That's the first equation that we wrote in this discussion. Okay. So then this J becomes E plus 1 minus alpha times G, and we know that this E, which is the emissive power, we know that this is the emissivity times the Stephen-Boltzmann constant times Ts raised to the power 4 plus 1 minus alpha times G. Okay, now we just need to substitute values. For instance, we know that epsilon, which is the emissivity, that is equal to 0.76. Sigma, we all know it is 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Ts, we know it is equal to 400 Kelvin. Alpha is given to be equal to 0.14. The incident irradiation is also given to be equal to 1000 watt per meter square. So if you just do the substitution, so basically you just need to do the substitution over here. And if you just substitute the values, I have already calculated this at my end, you will get your radiosity as 1963 watt per meter squared. Okay, that much is your radiosity. Oops. Okay. So you can now understand that the irradiation was equal to 1000 and your radiosity is equal to 1963, which is greater than 1000. So you can now appreciate that the 9663 watt per meter square, that much. So this part is because of the emissivity, which is basically this, and uh, so basically you cannot directly imply that, but at least you can now understand that so basically now you can infer that the radiosity is comprising of the fact that owing to its own surface temperature there is there is emission, which is the emissivity, which whose so you can individually calculate this and then quantify the emissivity. That's what I was actually trying to infer. But anyways, I hope you can now understand that there is a fraction of radiosity which significantly comes from the fact that the body itself emits radiation because of its own temperature. And also there is the reflected part which comes from this term 1 minus alpha times g. Okay. So you can individually evaluate these parts, and then you can see the individual contribution from the individual fluxes of interest. Okay. But anyways, we are just asked to calculate the radiosity. All right. So the second part is now rather straightforward because they are asking us to evaluate the net radiation flux, and now this we denoted as by q double prime rad, and this is quite simple. This is just j minus of g that we just now established, and we know that this radiosity came out to be equal to 1963 and the incoming irradiation was 10,000, which means that as so basically that 963 was the net radiative flux, which I was actually trying to say. But since there is a question, there is a dedicated question associated with it, that's why I just said it, okay, let's do it, basically do it formally. So again, this basically is nothing but the difference between radiosity and irradiation, and this just comes out to be equal to 963 watt per meter squared. Okay, so this amount 963 is, so basically what does it quantify? Physically it quantifies that it's nothing but the radiation that goes out from the surface, which is radiosity, minus the incident radiation that falls on the surface. So this much amount of radiation flux that is leaving a surface. Now you can understand that, okay, now we are kind of considering, so you can visualize this thing. Now we are kind of considering, let's say, a third body which is getting radiation that basically lives from this second body only. So then in that scenario, this net radiation flux that is leaving from this body of interest becomes the irradiation of the third body. I hope you can understand. So what I'm now trying to say is that, let's say now we are considering a third body, let's say this body, and our own aluminum plate was something like this. So we just now stated that this q dot red is equal to this 963 is nothing but the net radiation that is leaving this this aluminum plate. Now it may so happen that if this entire radiation flux gets incident on this third body, then this q dot red will serve as irradiation for this third body. That's what I am basically trying to say in this scenario. So I hope you can now understand that how this irradiation things actually comes. You can interpret this as a radiation flux coming from the surrounding. That is something I wish to clarify through this second exercise as well. Okay, I hope you can understand this from. All right, so we are now left with completing the third part. So I believe you are still aware of the third part. So in the third part, what they are saying is that because of this radiation, irradiation, and radiosities and net radiated fluxes, and also convection taking place from the ambient, you are required to determine the rate of change of temperature of the plate. That's what you are required to do. Okay, so so for this, what we'll do is we will we will choose a control volume that basically encompass this entire body. Okay, So this is basically our control volume of interest. Now, in order to evaluate what is the rate of change of temperature with time, what we'll do is we'll simply apply. So we'll just apply energy balance in the control volume. Okay. And that is simple, right? Because if you just apply energy balance, it will just give you that E dot in minus E dot out plus E dot gen is basically equal to the rate at which energy is changing inside the control volume. Now, what we'll do is we will consider the fact that the entire radiation is reflected through the net radiative flux. Okay, which means that although there is irradiation and then radiosity, but we will dump this contribution into the net radiative flux that is being emitted from the body itself. Okay, so in that context there will not, so this contribution from E dot in, this will just go up because we are dumping that contribution of irradiation into the net radiative flux. That's what we are doing. And of course there is no generation of energy taking place inside the body, which means I can then write that my E dot out basically becomes equal to E dot CV. See, we can also consider this, and then in E dot out you just need to consider the radiosity. Then this is what this is the second approach. So if you don't consider this to be equal to 0, then in the E dot out you have to only consider the radiosity part of the radiation fluxes, and then in E dot in you have to consider the irradiation times the surface area. But since we have already evaluated the net radiation flux, okay, sorry, so what I'm trying to say is that since we have already evaluated the net radiation flux and we know that this net radiation flux is from the body of interest, which means we can now consider this as an energy leaving from the body, and the contribution from the energy that is coming in is already incorporated into the net radiation flux. That's the justification that I would give here for considering E dot in to be equal to 0. Again, I would say if you don't consider E dot in to be equal to 0, then in this E dot out, you just have to consider J, and in this E dot in, you then have to consider G. Of course, since this is fluxes, you need to multiply it by AS. But since we are kind of, so since we have already simplified and calculated the net radiative flux, that's why we are kind of like, and we have observed that this is the energy that is going out from the body, and that's why we'll consider this E dot in to be equal to 0. Okay. So then what you can now do is, your E dot out now basically comprises of two things. First, the net radiative flux that leaves the body, which is Q dot double prime rad, which we have defined. And then there will also be one more source which will basically lead to energy transfer taking place from the body, and that is basically because from the convection. So this will be just Q radiation, Q double prime radiation plus Q double prime convection, and this will be equal to dE CB by dt. Okay, so if I basically write this nicely in the next phase, I can, of course there will also be a multiplication by the surface area of the body because these are just fluxes, and here we are just writing in terms of the rates, which is basically watts. Okay, so so if I write this little bit nicely, it just becomes Q rad plus Q conv times AS, and this is equal to dE CV by dt. Okay, now this dE CV by dt is nothing but the energy content inside the control volume, and multiple times we have witnessed the expression of this. This is nothing but the mass of the control volume times the specific heat times its instantaneous temperature, and then I can write it as the density times the volume, okay, times the specific heat, okay, and then this basically becomes dt by dt. All right, so what we'll do is we'll just now substitute this in this expression. So we'll get minus Q dot double prime rad plus Q dot double prime convection, and this is AS, and this is equal to rho times V times C by this. So what we'll now do is we will take this as to the denominator, and then we will get uh, something, and we'll see that. So this becomes this, and then this becomes, so we'll write this as rho times V by AS times the heat capacity times dt dt. So you can observe that this V by AS is nothing but LC, which is the characteristic length of the body, and this is L, and we know that this is equal to 5 mm. That is already given to us. Also, we know these quantities because Q dot rad is the net radiation exchange taking place. We know that this is equal to 963, which we have just now evaluated here. Okay. This is equal to 963. And this Q dot convection we can easily evaluate from the Newton's law of cooling, which is nothing but H infinity times the surface temperature minus T infinity. And we know this, right? Because H infinity is 40, then this Ts is 400 minus 30. Okay. Which means we can now formally, write that my dt dt is equal to minus of 963 plus 40 times 400 minus 30 divided by the density. So it is given that the density and the specific heats of the body are given as, so density is equal to 2702 kg per meter cube. Specific heat is given as 949 joule per kg Kelvin. So then it becomes the density, which is, so what's the density? Let's check it out. I mean, the value. So it is 2702 times the heat capacity, which is 949, times the characteristic length of the body, which is its thickness, and that is equal to 5 into 10 to the power minus 3. If you evaluate this, this will be your rate of change of temperature with respect to time with an unit Kelvin per second. That's it. So if you evaluate this, you will get this answer. So I have just done it in my calculator. So you will get it as minus of 0.378 Kelvin per second. The minus sign again indicates that if you plot T versus temperature versus time, you will get a decreasing slope, which means that your temperature is continuously decreasing with time, which is obvious because the surrounding is trying to basically cool the body. Okay, so that is precisely the expression of dt by dt. That's it. Oops. Okay. So that's your expression of dt by dt. That's it. So so I believe this is a good fundamental problem involving the four fluxes of radiation, and then we have also learned how to apply energy balance in incorporating radiation, and then to evaluate what basically that. So I hope you understand that this T is this T is basically the temperature of the body. It is not the surface temperature, because surface temperature is already known, and we know that this is the temperature that basically gets exposed to radiation. But this T is what dictates that what will be the temperature of the object, and what dt denotes, or what basically d of capital T by dt denotes, is that given that there is radiation and convection taking place, how does the temperature basically vary with time? Again, I repeat, we are disregarding any spatial variations, which means that we are not considering the fact that the temperature is also a function of space, which is again arguable, because you can evaluate the bio number, as I said, and you can see that if you calculate HLC by K for this scenario, you just consider K to be so this is an aluminum, I believe this is an aluminum object, so you can take the K of aluminum. If you calculate that, you will see that your bio number is actually less, in fact less than 0.1. So then you can disregard the spatial variations, as we did in case of lump body. So you can assume this body is a lump body. That's what I was trying to quantify. Okay. All right. So this concludes the discussions on the radiation fluxes, and we will now proceed with another important discussion, which is known as the intensity of radiation. And before that, I'll just let you to basically, go through the problem that you just solved, In the meantime, I will be back by filling my mug with some water, and then we'll continue the discussion on radiation intensity. I'll be back in just 1 minute. All right. Sorry for the interruption. So let's resume. So we will now formally define a quantity which is known as radiation intensity. And the reason why we are so interested in defining this quantity radiation intensity in addition to the fluxes is that we will later on see that the radiation that leaves a surface is actually a function of wavelength, because you understand that this radiation is emitted through electromagnetic waves, so it's a function of actually wavelength, and also it's a function of through which direction we are quantifying the radiation. Okay, so it then becomes important to define something which is known as radiation intensity, which in general is a function of wavelength and the direction, uh, meaning that if you look into spherical coordinate, direction means that it is just a function of theta comma phi, that is the polar and the azimuthal angles. uh, but uh, but in general, it then becomes important to define separately the radiation intensity, which you can eventually link with to the emissive power of that particular body. Okay, so again, you can ask me that why we are defining radiation intensity, because we can also define emissive power. You will see that actually the emissive power and the radiation intensity has subtle differences if we consider situations in general. But you can then say that they are related to one another if we consider certain assumptions. For instance, if you consider your body to be a diffuse body, meaning that your intensity of radiation, which we will define shortly, it is not a function of basically the direction, then you can eventually show that your emissive power, in fact, if I need to say it correctly, it's actually the spectral emissive power that will be basically 5 times the spectral intensity of radiation, and that's how actually the intensity of radiation which we will define is related to the emissive power. The reason why we are defining these two, because actually there, as I said, there are little subtle differences, and I would say that the most fundamental quantity of interest is actually not the emissive power, but it is actually the intensity of radiation. So emissive power actually comes from the definition of intensity of radiation, and that's why we will separately define this intensity of radiation. Then we'll try to quantify the emissive power. Okay. In fact, you can also prove the Stephen-Boltzmann law from these definitions as well. But we have already done that in the discussion. I mean, in the lecture series. So we'll not do those things now. Rather, we'll try to build up on the physics and I mean, we'll try to understand the physics associated with this, which will eventually help you, in solving the problems that you will get. All right. Having said that, what we will do is we'll consider a differential body whose area will denote it as by dA1. So this dA1 is basically this shaded area of the body, and this body is characterized by an unit normal n hat. And what we are now doing is we are looking into any generic angle. This theta is basically a generic polar angle that we are considering, and through this generic angle we are defining a area which we will call it as DAN, and this DAN is nothing but the area of the emitting surface normal to this direction, meaning that if we consider this surface basically emits radiation in all possible directions. And then what we are trying to do here in order to define this radiation intensity is that we are picking any generic direction characterized by theta, and then we are saying that what is the area that is normal to this emitting surface in that particular direction, and that area is given by this DAN. You can prove that this DAN is nothing but dA1 times cos theta. That's simple, because if this is theta and this is dA1, so this direction, the area of the emitting surface normal to this direction is just nothing but dA1 times of cos theta. You can appreciate that when theta basically is 0, which is when you basically consider the surface here. Okay, it is nothing but this surface itself. When you are moving the surface to any arbitrary generic direction, the normal associated, so basically the area associated with that particular normal is nothing but dA1 times of cos theta. Okay. Then, considering this scenario, you define something which is known as the spectral intensity of emitted radiation. It is denoted as I lambda E. This spectral intensity of emitted radiation is defined as follows. Okay, so it is defined. So from equation 1, you can see that it is defined as a quantity dq divided by dA1 cos theta, which is the normal area, times a quantity d omega and d lambda. We will denote this, or we will try to understand these quantities d omega and d lambda. First of all, we will try to understand what this d omega is. So this d omega is actually known as the solid angle that is actually being subtended by this normal area onto the emitting surface. Okay, so then this d omega is given by dan by dan by r squared. So this is what actually the solid angle this is how actually the solid angle actually look like. So this d omega is the solid angle subtended, as I said, and this dq is nothing but the rate at which the radiant energy is actually emitted at that particular lambda. So then, using these quantities, you can define the spectral intensity of radiation as the rate at which the radiant energy is emitted at the wavelength lambda in the theta phi direction in general of the emitting surface normal to this direction per unit solid angle about this direction and per unit wavelength lambda. Okay, about lambda basically. So this is the definition I took directly from the book of Incropera, and I hope now you can understand that this is nothing but the radiant energy that is emitted at a particular wavelength lambda, okay, per unit area that is in the direction normal to which we are basically looking at, per unit solid angle about the direction and per unit wavelength interval about d lambda, basically per unit wavelength interval d lambda about the wavelength lambda. So so what we can now do is we can also quantify this. So for simplicity, what we'll now do is we'll write this dq by d lambda as something which is known as dq lambda, and this is known as the rate at which radiation of a particular wavelength lambda leaves dA1 and passes through DAN. So then you can define this I lambda E, which is the spectral intensity of emitted radiation, as dq lambda by dA1 cos theta times d omega. Okay, so so that's the definition. So this is the most general definition of the intensity of emitted radiation. So this is the most general definition. Okay, or in other words, what you can do is you can write this rate at which, so you can basically write this d lambda q, which is nothing but the rate at which radiation is emitted, as the intensity, as the spectral intensity of emitted radiation times dA1 cos theta d omega. Okay, all right. And you need to understand that this d lambda e, which is the which is basically the spectral intensity of emitted radiation, this is a function of direction, which we will denote it as by theta comma phi, and it is also a function of wavelength in particular. Okay, and this d omega, as I said, is, and as we have already looked into in this week's discussion hours, is that in this week's lecture hours, is that this is the solid angle subtended, which is denoted as TAN by R square. Okay, so that's the complete definition of the intensity of radiation. I understand this is a little bit of more mathematical, but this is how, this is how it is actually defined, and you cannot, basically do anything just more than this. Okay, you need to understand this through this. You need to understand intensity of radiation through this very definition, very fundamental definition that we just now defined. But later on, things will be much more clear if we define certain things, as we will see very shortly. Okay. So I hope this is this bit is clear. So I'll wait here for a couple of minutes, just for you to uh, digest this thing that we just now saw, and then we'll look into an important definition, which is known as a hemispherical emissive power. Okay, so what I'm now trying to say is that you now need to understand that, so basically we are considering a particular surface which is emitting radiation. Okay, and so the area that is associated with this was dA1. Okay, and it is emitting radiation with some spectral intensity of radiation I lambda e. So then there is a term which people are generally interested in. This is known as the hemispherical uh, emissive power. So it says that out of the intensity of radiation that is emitted, which is a function of direction and wavelength, it says that what is the total, basically what is the total radiation that is emitted in all possible direction. And I hope you can understand that the only surface which will give you an idea of this total radiation that is emitted from this body. Oops. So the only surface that will give you an idea of the total radiation that is emitted from this body is basically a hemispherical that will encompass all the radiation that leaves this body dA1, which means this. So I hope you understand that this dA1 will emit radiation with some intensity of radiation in all possible direction. The reason why we are interested in the total emissive power is that we are trying to seek the question that out of this intensity of radiation, what is the total intensity of radiation that is being captured, okay, by a far away body, let's say. And this total intensity of radiation will be captured completely by a surface which will look like a hemisphere. And that's the reason why this is also sometimes known as the hemispherical emissive power. The reason we are considering this as a hemisphere and not a sphere is that because we are just interested in the top surface of this body only. Okay. And that's the reason why we are considering it as a hemisphere. You can now ask me that why are we not considering a let's say a semi cube or something like this. That is simply because we are just trying to build a fixacious surface which will, try to capture all the incident radiation, all, or you can say which will try to capture all the radiation that will leave the surface dA1, and the possible surface that can do so is basically a hemisphere. So then I can write this dq lambda as, so then I can write this basic. So what we are essentially doing is we are integrating this dq lambda over all the possible direction, which now is just sine theta d theta d phi, because this is the elemental area that we consider when we are when we are basically defining a hemisphere. Okay. So then the hemispherical emissive power q lambda, we denote it as by q lambda. This is defined as the surface integral of I lambda e, okay, times, so actually what we are doing is we are actually integrating this I lambda e here and defining this q lambda basically, which is the hemispherical emissive power. So this q lambda is actually integral of I lambda e, which is a function of theta, phi and lambda, and then this is dA1 cos theta times sine theta d theta d phi. Now you can, so basically you can think that why you are defining this sine theta d phi d phi. This is sine theta d theta d phi. This is nothing but actually the elemental area per unit. So basically what we are doing is this is, so actually you can show that if you consider a hemisphere, the elemental area of that sphere actually come out to be r square sine theta d phi. So the solid angle d omega that we are actually trying to seek here becomes das by r square, and then this just becomes sine theta d theta d phi. Okay. And that is actually from where this sine theta d theta d phi comes in. So we are just trying to calculate the solid angle. That's what we are actually trying to do. We are trying to calculate the elemental solid angle, then trying to integrate it over the entire, possible direction. So then I hope you understand that this integration needs to be carried out from theta equal to 0 to pi by 2, and from phi varies from 0 to 2 pi. The reason why we are doing is because in order to encompass an entire hemisphere, I hope you can understand that your z direction is something like this. Okay. And if I pick any radial, if I pick any radius of a sphere, I'll denote it as by r. Then your theta is basically this part, and your phi is actually the projection of this radius onto this plane. So your phi is basically this angle. So your phi is basically this angle. So it's basically the angle that we'll get by revolving around the z-axis. So in order to generate the entire hemisphere, you need to vary your theta from 0 to pi by 2, and you need to vary your phi from 0 to 2 pi. Because your theta needs to basically come from here to here, and in the same time your phi needs to go around this entire z-axis in order to generate a complete hemisphere. So this means that your so basically the integration that you need to do in order to define the hemispherical emissive power is, so your q lambda will be integration from 0 to pi by 2 and integration from 0 to 2 pi I lambda, which is a function of theta, phi, lambda, dA1 cos theta, and then this becomes sine theta, d theta, d phi. So now what we'll do is so this dA1 is just the differential elemental area of the object which is, emitting radiation. So then what we'll do is we'll divide this q lambda by dA1, and then this becomes integration of 0 to pi by 2, integration of 0 to 2 pi I lambda theta phi lambda cos theta sine theta d theta d phi. Okay. And this q lambda by dA1, this is actually known as so basically you can interpret that this is a flux. So this is actually known as the hemispherical emissive power, and we will denote it as by a quantity which is E lambda basically. Okay, and this E lambda, as you can interpret, this is a function of theta, this is a function of uh okay, this, so what you are now doing is you are actually integrating it over the entire possible direction. So this E lambda is essentially a function of lambda only. Okay, so basically the hemispherical emissive power, okay, which we will denote it as by E lambda, you need to integrate the intensity of radiation over the all possible directions, which will basically give you the hemispherical emissive power. So now you can understand the difference between the intensity of radiation and the emissive power. When we speak about the intensity of radiation, it means that it is a quantity which will depend on which angle we are looking at, or in other sense which direction you are looking at, and the particular wavelength we are looking at. But if you are defining the hemispherical emissive power, we are kind of saying that what is the overall contribution from all the intensity of radiation in the all possible directions. That's what the integration actually signifies, and that precisely gives you the hemispherical emissive power. So as I said, there's a subtle difference. This is the first difference that you will basically witness here. So E lambda is actually an integration over all the possible directions from 0 to 2 pi and from 0 to pi by 2. I lambda, which is the emitted intensity of radiation, which is a function of theta, phi, and lambda, sine theta. First of all, I think we should write the cos theta term. That is cos theta, sine theta, d theta, d phi. That's precisely the definition of the hemispherical emissive power, and this is a very important definition that you guys need to understand. Okay. Now there is, so this is the second thing that you guys need to understand. Okay, so now there is a particular kind of body which is known as a diffuse body. Okay, so if I have a diffuse body, the definition of diffuse body is that the intensity of emitted radiation is independent of direction. What it means mathematically is that my I lambda E, which was earlier in general a function of theta, phi, and lambda, I hope you can now realize that this will be a function of just lambda. Okay, which means physically that you pick that dA1 surface, that is the differential, area, and you look into any direction, the intensity of radiation will just be the same. Or in other words, it will not be a function of theta comma phi. Okay, in that context, if you use this expression for diffuse body, you can now realize that this intensity of radiation will come outside the integral for a diffuse body. Okay, so then for a diffuse body, you can define this hemispherical emissive power as just I lambda, because this will now come out of the integral, which will now be just a function of lambda, integral from 0 to 2 pi, integral from 0 to pi by 2. It is just cos theta, sine theta, d theta, d phi. And if you just do this integration, you will see that this integration will just give you a constant which will just be equal to pi. Okay, then you can reach to a very interesting relation which speaks about the relation between the hemispherical emissive power and the intensity of radiation for a diffuse body, and this is equal to pi times I lambda of lambda. Okay, and this is the relation that holds good for, so the only assumption you will consider here is that you are considering a diffuse body. Okay, so the most general definition of the hemispherical intensity or the hemispherical emissive power is this: if you now consider your body to be a diffuse body, which means that your intensity of radiation is independent of direction, and then you will reach the fact that your hemispherical spectral, so actually this is known as the hemispherical spectral emissive power because it has still a dependence on wavelength, but you will realize that the hemispherical spectral emissive power is equal to pi times the spectral intensity of radiation, which is basically the case for a diffuse body, where the intensity of radiation is independent of theta and phi, basically. Now, if you next ask me that, okay, the emissive power that we are considering here is nothing but the spectral emissive power. What if I want to define an emissive power which will take care of all the emissions for all wavelength? Then what I need to do is I need to integrate this expression for all the possible wavelength, okay, from 0 to infinity, where my lambda basically varies from 0 to infinity, and then this becomes pi times integral 0 to infinity I lambda, which is just a function of lambda d lambda. So this quantity is now known as the total hemispherical emissive power, and this is nothing but you integrate the spectral emissive power. If basically you integrate the spectral hemispherical emissive power in all the possible wavelength that it will that it may emit radiation, and then this is denoted as by E, and this is known as pi times of, we'll call it as I, and this relation is actually known as, so this relation basically gives you the relation between the total hemispherical emissive power to the total intensity of radiation, and this is actually written for a black body, so we'll write the subscript IB. So the total hemispherical emissive power of a black body is equal to pi times its total it's basically intensity of radiation. So when I say this this intensity of radiation, this is basically integrated for all the possible wavelengths. That's what we try to mean by this total hemispherical emissive power. Okay. So in physical in physical sense, what this EB actually tries to signify is that it is the rate at which radiation is emitted per unit area in all possible directions. And remember, this is true for a diffuse body. Okay. All right. So what we'll do is we will stop the discussion here. Up to this point, we have covered quite a bit of radiation today. So we began by giving a brief introduction of radiation, then try to understand the radiation fluxes, solve the problem associated with the radiation fluxes, define formally what is the intensity of radiation. Although I understand that the definition is a bit mathematical, but it is what it is. Okay, so there is no escape from that. But then at least we have tried to understand physically how do we define a hemispherical emissive power, and why do we choose a hemisphere, by the way. That's what we saw, and then looked into something which is known as a diffuse body, tried to understand that the intensity of radiation is a function of which direction we are looking at and what wavelength we are basically trying to associate it with. Okay, and formally defined the total hemispherical emissive power, which is equal to pi times the intensity of radiation for a diffuse body. Okay, so we'll stop here today, and we'll meet at the same time in the next week, and then we'll take it up from uh, where we left today. Okay, so please let me know if there are any doubts by posting it in the discussion forum, and till then we'll meet next week at the same time using the same link. Thank you guys.